I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
So welcome to episode number 60 of Physics Matter Colloquia series. So my name is Christine Darve and I work at the European Spallation Source in Sweden, and I'm also the former chair of the Forum of International Physics, the FIP, at the American Physical Society, which proudly support this series. So today in the panel, I'm delighted to have with us Alan Hertz, who is coming from Los Alamos, and Joe Nimela, who is from the ICTP, both of them also former FIP chair. So the Physics Matter Colloquium series is open to everyone curious about physics and to connect with the society. So over the past 5 years, we have explored topics that have to take us along the road. So inspiring by the major research infrastructure, such as the Sesame Light Source in Jordan, as well as educational theme around scientific discovery, particle accelerator, and international collaboration. So I invite you to visit our webpage and to join us for this sustainable CO2 neutral journey, through knowledge. So this fall, we have traveled across Africa, discovering and shaping the advances of key disciplines. So as part of this International Year of Quantum Science and Technology, we have been deepening our collaboration with our colleague of UNESCO. And I apologize if there was some last minute change this month with the program. So our virtual flight has shifted from Ghana to South Africa, but we will, however, go more and listen more to what happened in Ghana with this closing event, which is scheduled in February 26th, and especially while concluding this year Physics Matter Colloquium series on December 10 with Professor Ana Maria Seto, who is the chair of the International Year of Quantum, the steering committee of that Year of Quantum. So now I want to emphasize that last Monday, we co-organized a fascinating forum, which was held between the IUPAP, which is the International Union of Pure and Applied Physics, and the UNESCO. So that was the possibility to focus on the intersection of quantum technology and industries. So this event had featured speakers, from Microsoft, IBM, and several innovative startups. And among our invited guests was today's speakers representing Africa, growing leadership in quantum science. So it's my great pleasure to introduce Professor Yaseera Ismail, who leads the Q Photonics Lab in the Department of Physics at the Stellenbosch University, which is in South Africa. So Professor Ismail had her PhD at the University of KwaZulu-Natal, and she is an experimentalist specializing in quantum optical tools for long-range secured quantum communication. So her pioneer work has led to the first quantum satellite linked in the southern hemisphere and the longest intercontinental quantum secured link, spanning 12,900 kilometers between the northern and the southern hemisphere. So she served as the editorial board at Scientific's Report and in Optica Ambassador. So she has been like this, so already since 24. So she has been integrating into the South African Young's Academy of Science. So that was a really nice possibility for the younger to be represented. And she's also, so the Optica appointed vice president of the International Commission for Optics. So finally, we want also to congratulate her for winning the second place, so for the IUPAP photo contest. And this is this wonderful photo, and I think we'll see this a bit later. So for the logistics, so you have this Q&A, which is on the bottom of your screen, and you can prepare your question that will be answered after the 40 minutes presentation that you will give. So Yaseera, the floor is yours.
Thank you, Christine. Let me try sharing my screen. Okay, can you let me know that you're seeing my screen well? Perfect.
Yep.
So,
Yes.
thank you. So thank you first and foremost to the American Physical Society Forum on International Physics to give me this opportunity to unpack Africa's quantum future in terms of strengthening research and innovation capacity at your Physics Matters online colloquium. Thank you to Jonah Miller and Alan Hurd as well for the invite, as well as Christine Darby. So as Christine mentioned, this is the second prize winner of photo of the IUPAP IYQ photo contents photo at a glance, and we're quite privileged to have this win because this really showcases Africa's contribution to quantum technology, and more so this is the experimental site of where the 12,900 kilometer quantum link took place. So quite an honorable moment, and I am hoping that this afternoon I can unpack this research contribution for you. So we are all celebrating many events this year in celebration of International Year of Quantum Science and Technology, focusing on the development of 100 years of quantum mechanics, but more importantly, to raise awareness of the importance of quantum science and technology in everyday life. And we just heard that the end of the International Year of Quantum Science is going to be held in Ghana in February of 2026, and it felt like the year of IYQ went by so fast. But I would be remiss if I didn't start off with the slide of the opening ceremony of the International Year of Quantum Science and Technology, which took place at the UNESCO headquarters in Paris. And I was honored to be part of the panel on public engagement and education. And the reason I mentioned this during this discussion is because one of the key insights that came out of the opening ceremony was inclusivity, not creating a quantum divide, and ensuring that all countries have a quantum initiative or is involved in the development of quantum technology. And so for that reason, today I'm going to share with you South Africa's quantum technology initiative and give you some insights on what South Africa's focus is in this quantum initiative. And so if we look at the quantum efforts in terms of funding worldwide, South Africa is a very small player, only about 45 million rands, about roughly $3 million contribution towards the development of quantum technology. However, we have used these resources very well to kind of develop technology that positions us to actually help the African continent as well. And so if we look at the South African Quantum Technology Initiative, it was supported by the Department of Science and Technology and Innovation back in March of 2021, when they approved the first round of funding of the initiative. And now we're actually starting the second round of funding for this initiative. When we started the initiative, we started with the 4 focused universities that focus strongly in quantum technology, with the aim of spreading out this initiative to other universities that can be considered emerging centers in South Africa. So South Africa has 26 universities, and the focus of this initiative is to try and ensure that quantum research is undertaken at most of these universities in South Africa, either by having a node of their own or by collaborating with existing strong nodes that have a strong quantum focus. And so if we look at the 4 strong nodes or the 5 strong nodes, we have a node at Wits University where the director of the South African Quantum Technology Initiative sits. And then we have nodes existing nodes at University of KwaZulu-Natal, which is my former university, and Stellenbosch University, where I'm currently based. And we also have a node at the University of Zululand and a node at Cape Peninsula University of Technology. And so we're hoping that now, with this initiative going forward, we can expand this to other universities in South Africa as well. So if we look at the mandate of the South African Quantum Technology Initiative, we have the 3 focus flagship areas, which is the quantum communication flagship, quantum metrology, sensing and imaging, and then the quantum computing flagship. So from the start, when we started developing the white paper for the South African Quantum Technology Initiative, we knew that we have limited resources. And so we took a decision from the start not to put any resources into the development of a quantum computer. We focus only on the development of quantum algorithms that can be implemented on existing cloud-based quantum computers through collaboration. And a lot of our efforts in terms of development of technology is focused in the quantum communication flagship as well as the quantum metrology, sensing and imaging flagship. And one of the focus is then to take technology out of the lab towards deployment and then further towards commercialization. And so if we look at the emphasis of where we are and what we want to do, well, besides developing technology and progressing towards commercialization, one of the strongest focus in the Quant initiative is building skills and critical mass. So we have identified that if we have to compare South Africa to other countries in Europe and the US, we have a very small quantum research cohort. And so if we want to really be able to focus on the development of quantum technology and have industry uptake quantum technology, we have to really build our skills and our critical mass. And so a lot of focus is on emerging leaders as well as postgraduate studies in order to build human capital development. A lot of the focus is also on quantum infrastructure in the sensing and communication flagships to kind of create an environment for quantum technology uptake. Right now, we don't have a very strong quantum industry. And so hopefully through this initiative, we are partnering with industry to look at possible solutions for quantum and to build a quantum ecosystem to encourage quantum startups that spin off from our existing nodes and to try and create a quantum industry. And then, of course, one of the other focus is how can we take these technologies and interface with converging technology platforms. And so going forward, in the second cycle of our funding that starts this year, we're looking at exploring more nodes, looking at advancing more emerging leaders, especially at non-existing nodes, and then looking at more industry engagements to create critical mass and develop a quantum workforce. We have identified that this workforce will not come from only physics, but from engineering, from computer science. And so we really want to push the development of partnerships with other disciplines, partnerships nationally, as well as partnerships internationally. And so today in this talk, I'm going to be focusing on one of our international partnerships, which have led to this breakthrough of this quantum satellite link of 12,900 kilometers. And so, as Christine said, I head the Q-Photonics lab at Stellenbosch University, which is basically focusing on advancing quantum optical systems for quantum communication. And so within the lab, we look at different research areas that we focus on. We focus mostly in free space quantum communication, and we look at characterizing free space systems, as well as dealing with the effects of atmospheric turbulence, which poses a major challenge when we're looking at free space quantum communication. We look at development of single photon sources, especially in the presence of atmospheric turbulence, how to mitigate these effects. we got a strong focus of also looking at structured light and how we can create high-dimensional states that can be encoded, and the effects of atmospheric turbulence on these high-dimensional states. And of course, we are at this fourth industrial revolution, which is this AI revolution, as well as the second quantum revolution. And so fusing these two is a good overlap. And so we use machine learning to also monitor in real time free space links for quantum communication. And then, of course, the most recent development of the quantum satellite link between Stellenbosch University and University of Science and Technology of China, which has led to the longest intercontinental link, as well as the first quantum satellite link in the Southern Hemisphere. And so if we have to unpack then quantum communication, we have challenges both in transmitting single photons in optical fiber, as well as free space. So we know that if we look at current encryption techniques, it's based on mathematical algorithms. Quantum communication, however, uses single photons as carriers of information. And the whole aim is that we must be able to encrypt these single photons, but also ensure that these single photons survive the quantum medium in order to produce a secure key. In terms of fiber as a quantum medium to transmit single photons, it is very much limited in distance. And the reason why is because if we look at the fiber wavelength of 15 nanometers, the attenuation loss per kilometer is about 0.2 dB, which means after several hundred kilometers, you have the challenge of whether the photon will actually survive the quantum link. You're also limited in encoding when it comes to fiber-based quantum communication because polarization, optical fiber is very birefringent, which means polarization is not an ideal option for the encoding. And so you are limited in that aspect as well. In free space, you have atmospheric turbulence, which is a major challenge, but you have to find ways to mitigate the effects of atmospheric turbulence, and increasing the link distance can be also a challenge if you're going ground to ground. But if you're moving towards satellite, this is more opportune. If we look at where this field is developing, there is the strong drive globally to develop a quantum internet. But this would mean that we require the development of inter and intracity quantum communication links, which is what we're seeing occurring right now. A lot of research deployment in the field of quantum communication is going into the deployment of quantum key distribution systems between cities, within cities, and in our case, between countries. And so there's a lot of now deployment and development in this area of developing inter and intracity communication links. And the reason why is that there's a strong focus towards this development of what is known as the quantum internet. But of course, there's challenges. And one of the challenges that we have to think about is how do you increase the distance as well as increase the key rate? And we know that as you increase the distance, the key rate is subjected to atmospheric turbulence, or the single photons are subjected to atmospheric turbulence, which reduces the key rate. And so if we want to develop a quantum network one day that will lead to this quantum internet, we very much need to increase the distance of the quantum link as well as the secure key. And if we look at all these technologies that we've discussed, quantum communication, quantum sensing, as well as quantum computers, there is this drive to develop a distributed network of all these technologies, and pivotal to this network would be satellite links. And so we really have to think of how to develop quantum satellite links in order to just create this quantum internet as well as this quantum network, as it's going to be a pivotal part of this entire network. And so this led us to actually entering into collaboration with University of Science and Technology of China back in 2019, with the strong focus of implementing the first quantum satellite link in South Africa. And so we partnered with Prof. Jerry Pan and Prof. Zhang Yin at the University of Science and Technology of China with the hope of an intention of developing the first quantum satellite link. Unfortunately, this was pre-COVID, and so a lot of our timelines was affected by our inability to access labs. But eventually last year, we were able to implement this link, and which led to the first quantum satellite link on the Southern Hemisphere, which was exactly on the 13th of October, 2024. And so for the remainder of this presentation, I would like to take this opportunity to unpack this quantum satellite link and share some of the insights on how this link occurred, as well as some of the outcomes and results from this link and the achievements of this link. So if we look at launching satellites in general, we know we can launch satellites into the lower Earth orbiter, which is approximately 500 to 2,000 kilometers away from the Earth. We also have this opportunity of launching satellites into the medium Earth orbiter and your geostationary Earth orbiter. And a good example of a classical satellite in geostationary orbital is your connection to, for example, DSTV, which is a satellite which basically broadcasts. If we look at where we are in terms of quantum landscape, currently countries are heavily investing on the launching of these quantum satellites, but currently we can only launch them onto the lower Earth orbiter. It is quite a challenge to launch satellites to the medium Earth or the geostationary Earth orbiter. And so there are various countries that are investing heavily into the launching of quantum satellites in order to deploy quantum satellite links. Through our collaboration with the University of Science and Technology of China, we initially started off this collaboration with the intention of using the Messier satellite that was launched back in 2016. However, during the collaboration, Jinan-1 was launched, which is the current microsatellite that was launched by USTC. And so our quantum satellite link that was implemented on the Southern Hemisphere was implemented using Jinan-1 instead of Messier's. And so if we look at the feasibility of deploying these satellite technology is quite expensive. And so if we look at this going forward for researchers on the African continent, I think that the most plausible way of actually implementing quantum satellite links right now is through international collaborations. And so if we look at the first quantum satellite links that were implemented, they were implemented by the University of Science and Technology of China through the Messier satellite. And this basically was a pivotal point in the quantum communication landscape, for global landscape, because it showed for the first time that it is possible to perform quantum key distribution from a satellite down to an optical ground station. They were able to show that they could implement a downlink, so sending single photons that are encoded from a satellite down to an optical ground station, as well as an uplink. Furthermore, they were able to show that they were also able to perform entanglement distribution and share secure keys over distances that separate two optical ground stations. And this really opened up the opportunity to look at the deployment of quantum satellites and quantum key distribution links via satellites. And so, as I mentioned in the start, one of the challenges is ensuring that you can increase the distance of your quantum satellite links, while still ensuring you have a high secure key rate. And so when we look at the data that came out of the Messier satellite, you can see that the shifted key rate decreased tremendously with distance, because at 645 kilometers, they were obtaining a secure key rate back in 2016, 2017 of 12 kilobits per second. However, as you increase that to double the communication link of 1,200 kilometers, you reduce that 12 folds to 1 kilobytes per second. So you can really see that as you increase the quantum communication link, what you actually give up is the rate of your secure key. It really diminishes. And so that was back in 2017. However, this was the first time it was possible to show that quantum satellite links can be deployed for quantum key distribution. Back then, of course, there was the China-Austria link, which was the 7,600 kilometer link between Anton Zeilinger's group and J.B. Pan's group, that was implemented in 2017 and published in 2018, which again was the first time you saw a realistic application of quantum key distribution, because here in this case, they encrypted back then a Skype call. Now we use Zoom and Microsoft Teams, but back then they were able to encrypt a Skype call from the 7600 quantum key distribution link. And that showed the first time that it is feasible to apply these quantum key distribution systems to practical implementation. So if we look at both the Messias and Jinan-1, which was recently launched, both are launched into the lower Earth orbital and both sit about 500 kilometers away from Earth. And so Jinan-1 was launched now in 2022. And the difference is Jinan-1 is a microsatellite, while Messias is actually weighs 600 kilograms. And it's a satellite that basically has a quantum payload of 250 kilograms. Now, when Messias implemented the first quantum satellite link, they had this window period of 6 minutes in order to send single photons from a satellite to the ground station in order to produce the secure key. However, because they were using microwave bandwidth for the post-processing, it took 2 to 3 days to produce that sifted secure key. With Jinan-1, it's a real-time QKD process, so the experimental time still for transmission of your quantum bits is still 6 minutes. However, due to optical bidirectional communication, the secure key can be achieved in real time. And hopefully I can unpack this for you in this presentation. Okay, so Jinan-1 is the first microsatellite. As I said, it only weighs 100 kilograms. And the quantum payload weighs about 85 kilograms, if I'm not mistaken, or if not less. And this shows the miniaturization of the satellite from the initial Messias satellite. And as I mentioned, this is on an optical bidirectional communication, and that allows for real-time quantum key distribution. So here you have the 850 nanometer quantum communication link, which transmits encoded single photons that are decoy state QKD protocol down to an optical ground station. At the optical ground station, the polarization states of these photons are measured in the rectilinear basis, which is your horizontal vertical basis, or your diagonal basis, which is your plus and minus anti-diagonal basis polarization states. And this information is carried back to the satellite using a 1538 nanometer laser. At the satellite, basis reconciliation occurs. So for each photon transmitted, at the satellite, there'll be a confirmation if the same basis was used to encode the information as that measured will take place. And that information, again, is sent down to the optical ground station using a laser of 850 nanometers. Using this information of the basis reconciliation, at the optical ground station, the quantum bit error rate is deduced and the secure key is achieved. And so this experiment was implemented at various positions on the northern hemisphere, and in the southern hemisphere only in Stellenbosch, at Stellenbosch University in Stellenbosch in South Africa. So as I mentioned, the bidirectional communication was very important here as a way to actually ensure that we have real-time QKD. And this allowed us to produce a key within a few minutes of the transmission. So after the transmission of 6 minutes and a latency of about 2 minutes, the secure key was obtained, which could be used with an one-time pad to encrypt information. So here's the experimental site at Stellenbosch University, the setting up of the optical ground station. As I mentioned, that last year, October, was when we actually went live with our quantum satellite link. And on the 12th of October, we wanted to test whether this optical ground station was going to be able to track a moving object well in order to track the satellite. And so at that time, the International Space Station was passing over Stellenbosch. And so on the 12th of October, we tracked the International Space Station in order to check if we were going to be able to track a moving object of the satellite the next day. And you can see this is an image of the International Space Station from the telescope. Unfortunately, it's a bit hazy, and this is because on that particular night, the humidity was quite high, and there was a lot of water droplets on the lens of the telescope, which added to this unclear image. However, going forward, we had mitigated for the effects of the humidity, and the humidity improved, and so we were able to get much better results for the duration of the experimental implementation. So the satellite is launched sun synchronous, so meaning north to south, it moves north to south or south to north, and it's passed through at various times, okay, so I must admit this is data only for Stellenbosch University, and you can see on the various days, it passed through at Stellenbosch once at night and once at day. Since we can't really implement quantum key distribution during the day, we're only implementing at night. And so we had a 6-minute window period at which we could track the satellite. So we would have to track once the satellite was 10 degrees above the horizon, and then once it was 10 degrees again below the horizon, we had the tracking stop. So it was a 6-minute window period in which we could track and implement the quantum key distribution process. And so we did implement this for numerous nights. The 13th of October was the first night of the implementation, and we were able to get good results. It was not excellent because of the high humidity. However, that improved as the days went by. Important, however, was the elevation angle of the peak when the satellite was at its peak. And the higher that elevation angle, the better was the secure key rate. And so on the 20th and the 21st of October, we got much better results. And so, yeah, some of the data, so I present some of the data from the experiments. As I mentioned, they tried this at various positions and locations in the northern hemisphere. You can see this is an urban city, Beijing, which is a very populated city, and then a mountainous area. And then here's the data for Stellenbosch, and I'll go through it just now. What is important to note first and foremost is Stellenbosch University is basically embedded in a mountainous region as well. It is surrounded by the Stellenbosch Mountains, but the advantage of Stellenbosch itself is that it doesn't have any industry around it, so there's less pollution from industry. So that results in much clearer skies. And so on the 21st of October, we were able to achieve over 1 million bits of secure key during a single transmission of the satellite over the optical ground station. So as I mentioned, elevation is also important of the satellite as well. And so here we see that the highest on the northern hemisphere was roughly 592,000 bits. However, in Stellenbosch University, we were able to achieve the highest secure key of over 1 million bits with Jinan 1. So it was quite groundbreaking that we were able to achieve this on the southern hemisphere, the over 1 million bits, and the highest with the Jinan 1 satellite. Of course, as I said, the elevation angle is very important, and you can see the higher the elevation angle, the better the secure key. So once we achieved the secure key, we linked with Beijing. Beijing used a secure key that they achieved from their satellite, from their optical ground station. We used ours of the 1 million bits that we achieved. We used the one-time pad, so modulus with the one-time pad to encrypt an image to send to China, and China sent an image to us. And so the image that China sent to South Africa was the Great Wall of China. The image we sent to China was the experimental site where the link was being implemented. And so this showed that you can use the encrypted keys that we achieved from this whole link in order to encrypt information. So what are some of the milestones that was achieved? Well, this was the first link on the Southern Hemisphere. And, I mentioned from the start, it's important that we collaborate, especially when we want to drive quantum technology, because through collaboration, we really can push scientific advancements. And so this was the first link, quantum satellite link in the Southern Hemisphere. It's also now the longest link between two countries of 12,900 kilometers. It's the first link between the Northern Hemisphere and the Southern Hemisphere. And the highest secure key with Jinan 1 was achieved right here in Stellenbosch University. In terms of
Hello? Joe, are you there?
Yeah, I'm here. It
Uh,
seems like Yaseera had a bandwidth problem.
yeah, it looks like we lost the link. So indeed, quantum and numeric should.
Yeah, we had the longest one, but
That's an interesting aspect. So let me just make
I
sure.
just sent her a note and maybe she
You
can.
did. Very good. Okay. So she's got the Zoom link as well. So sorry for that. We don't know exactly what happened. But I guess this is those technologies. So we need to find a way to secure everything. So I apologize for that. We will just reconnect in few seconds. Yes, she's here. Perfect.
Sorry, Christine, I'm not sure when I got cut off. I apologize.
No problem. I hope it's yeah.
Yeah, I'm so sorry. I apologize. I think the internet at the hotel is not the best. I apologize for that. I hope I was on the slide. I'm not sure which slide I got cut off at.
I think you
Was
were
it
on this
this?
slide. Yeah.
This one
Okay.
is
Sorry, I apologize for that. Okay, so just to take you through the slide again, I apologize again. One of the biggest upgrades was the fact that you can perform now bidirectional key distillation using a laser as opposed to a microwave, which takes 2 to 3 days. Using the laser-based system, you can implement real-time quantum key distribution. Also, the optical ground stations are much more portable and weighs only 100 kilograms as opposed to 13,000 kilograms, which means that you cannot really make those systems very portable. So in terms of what does this research really lead to? Well, for the very first time, it was possible to use portable optical ground stations and a microsatellite to perform quantum key distribution. So this really shows that it's possible to scale up to develop a quantum network by being able to distribute these portable optical ground station at various key locations and strategic positions. We can create maybe a practical quantum constellation that can result in this global quantum network one day. I apologize again for my internet, and I would like to say thank you, and I welcome all questions.
It was very, very clear and fantastic explanation. So thank you so much. So again, no worry with the problem. Indeed, the technology is always the challenging part. So hopefully we'll have some possibility in the future as well to improve it, thanks to this quantum technology that you are providing and handling. So thanks a lot. So we will start the different question and answer. So we will let you a bit of time to write them in the question and answer box. Maybe, so if you don't mind to stop sharing, then I can read the first question from our colleague. So Alan Hurd had to leave, but then he was also fascinated by your presentation. And he was asking as well, so that you mentioned that there was a high priority for South Africa to be developing quantum algorithm. So that's what you mentioned at the beginning. So how will South Africa train quantum scientists and engineers for that task? Will the quantum program, the algorithm program, involve international collaboration as what you're doing for the satellite? That would be his
Thank
question.
you so much. Thank you so much for the question. So yes, I did mention that the focus is on quantum algorithms. So I can tell you at Stellenbosch University as an example, and this applies to other universities in South Africa as well, we have a very strong program for quantum research and quantum technology at honors level. And so from honors level, we try to train the students to work on quantum systems, so quantum computers that are on the cloud. We give them the basics on quantum technology, which then they advance further into a master's and a PhD program. And so they train to develop these quantum algorithms. We are also associated with GESTA's Open Quantum Science Initiative to further train the students. South Africa is also a partner of the Q South Africa, which is a part of the Q Cousin, which is part of Q World. And that is also to train students to use the access to open access quantum computers in order to basically upscale and then learn and thereafter develop their own technology, quantum algorithms. So for an example, one of our PhD students is looking at pulsar detections based on quantum machine learning. And so they're developing these algorithms to look at pulsar detections. And that's just one example of what some of the algorithms the students are developing.
That's an excellent answer indeed, and way forward. So indeed, that would be the question that I would have as well with the AI, and how much as well could it be improved, and can it be also, for instance, for the case of humidity, making as well some, I guess, distorted image as well. So is it like what you are using and what you are going for AI?
So we do that. Yes, we do incorporate that into our research activities within my lab as well. And so you see the structured light that you saw in the images, those are images that have already passed through atmospheric turbulence. So we simulate that as well in the lab, as well as we simulate that in order to produce enough data to apply to a neural network to use deep learning techniques to monitor quantum channel and look at real-time mitigation of atmospheric turbulence. And so we are actually implementing these types of activities currently.
Okay, very good. So we have so one question as well from so James Endicott, who is asking after this fascinating talk. So the comparison between so the two satellites, so Minsius and June-1. So it's very interesting. So however, it's not mislead that there is not many examples of those QKD distribution. Sorry, so at the moment. And that the launch of the Misuse has not been motivated a host of development, so in terms of the mission, so by other countries. So why is that?
I won't say that it hasn't been a motivation. Other countries are deploying quantum satellites. It's the struggle of actually implementing the quantum key distribution process. So I know at the National University of Singapore, the group of Alexandra Ling is also deploying quantum satellites. The challenge is the key distribution. In the UK, there's a massive effort into the deployment of quantum satellites. So it's not a matter of countries not deploying satellites. I think it's performing the quantum key distribution is difficult. And I think that if they can achieve that process, then we'll have a lot more satellites that are launched to be able to perform quantum key distribution with optical ground stations. So there are other countries implementing.
Very good. So we have another question from Gilbert Maid asking about, he would like to know, so what approach is used in case of satellite communication for generating so single photon? So is it attenuated laser or what's the way?
Yeah. Thank you. So if we look at the two satellites that was mentioned, Messias had two quantum payloads, so two single photon source, one to implement entanglement based on BBO crystals, so nonlinear optics, and it also contained a source of decoy state QKD, which is a weak pulse um, packet, which is attenuating a laser source. But decoy state in order to ensure that you reduce the attacks on photon number splitting attacks, right? In terms of Jinan 1 was also an attenuated laser source that implemented decoy state. Now, the difference between Messias and Jinan 1 is Messias had 8 lasers deployed in the quantum source to implement the decoy state protocol to control the vacuum state, the signal state, as well as the decoy states. In Jinan 1, only one single laser was used to produce the decoy state protocol, but was able to implement all the different states that was required to perform the QKD. But it's an excellent question.
And an excellent answer. So indeed, you need all the equipment and the way to handle it. So with now, so James has also another question, which is, what is required to get to the next stage of inter and intra-city communication? Is it feasible, so in the 5 years timescale?
So first answer is going to be resources, right? You're going to have to need resources. If we look at fiber-based quantum communication, this is commercially available at the moment. You can go to companies like, for example, IT Quantique in Switzerland. You can buy a device, you can install, and you can perform QKD over 150 kilometers, let's say. So it's technology that's readily available. In terms of increasing the quantum link beyond 150 kilometers for fiber, you're going to have to use a trusted node system, right? Just like between the Beijing and Shanghai of 32 trusted nodes to create a 2,000 kilometer QKD link. In terms of feasibility, I think that the know-how is there. I think the resources is required. And if you have enough investment, whether it's investment from government, investment from industry, investment from corporate, we can aim in the next 5 years to have intracity and intercity communication links. I just think it comes back down to resources.
Good. Now we have also another question, speaking about hardware, from Marcel Yumko, who is living in Congo, and he has been published physics books at the CIRT, and this is on the subject of matter on density change. So he would like to know, to make an experimental, with a high mechanical waves of frequency, some gigahertz. So is your institution able to support those experiments as a pilot project? So international collaboration potential?
I think that he needs to contact us and we can discuss further how to go about collaborating on such projects. I think there's many opportunities, and as I said, breakthroughs in science comes with collaboration, and we all need to work together with common goals. So please feel free to reach out.
And you would have those equipment potentially with gigahertz?
Yes, we potentially do have. We have a very strong optics and photonics group at Stellenbosch University that are working in numerous research applications.
Very good. And we have maybe with Leo. So I saw that your hand was up. Do you want to ask the question live? He is not there, allowed to talk. So maybe Galileo. So if you want
Yes,
to ask a question,
I can make the question speaking, but I also wrote if you want to read it's the same. What I would like to say is the following. At the beginning, you showed the world map of quantum initiative. That world map reminds tremendously that for synchrotron distribution worldwide. For synchrotrons in Africa, there is a very important initiative. My question is, your initiative, how much is national and how much is open to African collaboration?
That's a very good question. So right now, there is a strong focus to develop South African systems. So it is a national program, right? But we do have other initiatives. For example, Joe would also know about the African Laser Center, where South Africa strongly is driving as well, where we train postgraduate students. We bring these postgraduate students from other universities across the African continent to work in our research labs. We fund them. And so they then get the advancements and they then take that skills out of South Africa to their own countries to further develop their technology and their skills to other researchers in their country. So as much as the South African Quantum Initiative, there is a strong focus on South African nationals, but there are other centers and other initiatives in South Africa that helps African researchers as well. I hope that answers, but we do try our best to help the African continent.
Yeah, I think it was a good answer as well. And indeed, this is for the synchrotron. Now for the neutron source, indeed, the use of neutron for the quantum, we discussed this aspect as well during the forum last week. So I think it was complementary and multidisciplinary. I mean, in some sense, knowledge in quantum is essential and can be applied in many aspects. So with this example, potentially, could you give some of those examples of successful cross-section collaboration as well that could be developed? So this one maybe with Congo, as we see, so that could be developed today,
No.
or you already have some thought?
So, we are at this moment on the quantum algorithms. We're training a lot of computer scientists to work with quantum physicists because we strongly believe that if we look at these technologies, it's not only physics, right? We need other disciplines, interdisciplinary research to really drive technology advancements. And so in the quantum algorithm space, we're really trying to focus on bringing students from mathematics, from computer science into the honors program to take these courses and then further upskill in order to then start looking at quantum algorithms. Obviously, quantum communication is not just a physicist, it's an engineer, it's a mathematician, it's a computer scientist. So again, there's a lot of interdisciplinary. One of my goals this going forward is to bring more African countries into the space. And there is initiatives happening on the African continent. For example, AIMS is now has a quantum flagship as well, where they're trying to also upscale their master students to understand quantum algorithms. And so this is associated quite a few countries across the African continent, like Rwanda, Ghana, all part of AIMS, which is now has this quantum lead program. And so we're really trying to focus on collaborative efforts. And hopefully going forward, we'll have much more examples to put forward where we can even solve some local problems.
Indeed, the field of mathematics and applied mathematics, and as well in Stellenbosch, this is, I think, where you work with this concept, so with the CS for computational science, and a lot of development in that field to apply in the different technology. So that's really, really interesting, and the connection as well with AIMS. So on the African Institute for Mathematical Science, this is also the important aspect. Joe, so we have a question from Joe.
Yeah, thanks a lot, Yaseera. That's really wonderful. So at least up here in Europe, there's quite a few startups now in the algorithm business, and they're small, but they're with the kind of resources that also could be make them available in other parts of the world. So do you also have that sort of environment in South Africa where you're starting to see startups and simulation software, quantum simulation?
Very slow. I'm not going to lie. We really hope to learn from Europe, and particularly also the UK on how they built up their quantum ecosystem when it comes to quantum startups. We actually did a knowledge exchange the beginning of this year where we went to the UK and we actually chatted with the different institutes in the UK, specifically the quantum startups, to see how they started off. Because one of our biggest challenges right now is getting that ecosystem building. And so we're really hoping to learn from other countries that have been successful in quantum startups. One example I can tell you, it's not really taking place in South Africa, but we had a student that graduated at a university in South Africa. He then moved to Canada, and he's got a flourishing quantum computing startup that looks at drugs delivery, so pharmaceutical drugs. And he's now raised several million US dollars for his quantum startup. But of course, he started off in South Africa. He left South Africa to start his quantum startup in Canada. But this is something we're trying to develop in our country, and we're really looking at learning from other countries on how to develop our quantum ecosystem there.
Great, thanks. Thank you.
Indeed, it looks that Canada is very dynamic as well. And we had the example, so during our last forum, so with so another speaker as well that was moving some from Cameroon to the Perimeter Institute, so in Canada. So, but that's another part, I think, of Canada that you're speaking about. And I put the link as well in the chat from the presentation as well we had last week and the recording that will be available and that will follow up in the other IUPAP UNESCO link. So please take note on that, and we will have it also listed there. So we have another question that arrived. From Gilbert Maé. So speaking and asking, so he's from Senegal, and he recently graduated, so with a master's degree in physics in France, and he's very proudly, he's interested so in the research topic and would like to know, so if currently, so you have any PhD opportunities available.
I actually do, and currently there's an open call for the ALC scholarships as well. And so if you're interested, reach out to me. We maybe can apply for an ALC scholarship, and you would qualify since you're from Senegal, and you could probably come through and spend the next 3 years in Stellenbosch University. So just reach out to me and let's discuss your research opportunities and where you are, what field you have been working on in your master's.
That's really nice. And we see that we have other person from Senegal here as well with Professor Oumar Ka. So I don't know if Oumar, you want to speak? I force you to speak maybe.
Hello.
Yeah, it's so nice to see you. So sorry. So because I heard the Senegal, so I wanted to take this opportunity to underline all the work that you are doing as well. So with the IUPAP as well, so together with the ASP, all the work that you've been doing there. So to really emphasize all the collaborative approach that you have been working on. So thank you very much, Professor Omaka. Even being retired, so we see that active and dynamic. So if we can hear a few words from you, it would be a pleasure.
Well, that was it's a great pleasure that I listened to this presentation, and this led me to having a few ideas that will probably I think about getting in touch with our colleague and see what could be done with Senegal. Yeah.
Perfect. This is exactly what we want. So opportunity like this to collaborate. And thank you again for everything you're doing.
You're welcome.
We definitely want more collaborations. And I mentioned to Christine when we were chatting earlier on that 2 years ago we hosted the Optics and Photonics in Africa conference, which was an inaugural conference that Joe also knows about. And the whole aim of that conference was to bring researchers from the African continent to South Africa to look at possible collaborations. And we're always interested in collaborating.
Excellent. Indeed, collaboration is what makes everything being more accurate and bringing as well science and technology to its reach. Thank you so much. So we have, let's see. So wondering as well if they are in master's, so for a master's degrees, any kind of scholarship opportunity. So I think, I don't know if you know, or should we share later on information?
Yeah, share later on information so that everyone interested can get access to information.
Excellent. So I think it was the perfect way just to look at the future generation being trained. So the mathematical aspect, so all those computing science, the technology to be able as well to host such type of algorithm, and all the motivation and as well the passion that people like you would have. So thank you so much for everything you presented to us today. And you see, so it's bring as well different bells everywhere around the world, and especially in Africa. And this is how I think so. Again, I would like to thank you for this wonderful presentation and opportunities. And it brings us indeed to look at collaboration within Africa. So by presenting next, so Physics Matter Colloquia, which will be on the 20th of November, and this time, so we will be aligned in time as well, so on the planet. So we will have a possibility to hear more about this African strategy for fundamental physics and application. So this is with our guest speaker that you see here. So I will not name all of them, but with so Professor so Petra Rudolph, with Ulf, who is as well listening as well today, co-found, and then with Munia Lassina and Professor Ketavi. Together with our colleagues from Africa. So it's really important that we stay tuned, we stay connected, and we try to see how to get the better understanding of a strategy that could impact Africa and all the rest as well of the planet. So thank you very much for today's and for listening and for sharing the world. So we stay tuned for the next Physics Matter, because I think it does matter. Thank you very much. Bye, everyone.
Thanks.
Thank you.
Thank you.